Okay, section 3, we're going to start with the example on page 154 on the top, but my smartboard is not responding here to some things. I think I can write on it. So I'm going to be walking back and forth to the computer to move things, so my voice might get a little low. You might have to turn up the volume as you listen to this. So we're going to start with the example on the top of page 154 to get an idea of what's going on with linear programming, feasible regions, right? So optimizing with linear programming, and an electronics company produces digital audio players and phones. A sign of the company bulletin board is shown below. If at least 2,000 items must be produced per shift, how many of each type should be made to minimize costs? The company is experiencing limitations or constraints on production caused by customer demand, shipping, and the productivity of factory. A system of inequalities can be used to represent these constraints. So you have constraints that are going to be basically linear equations, just like in section 2 when you were looking for the points of the vertices. It's essentially doing that same thing over again, but to minimize costs. So the minimum value is going to be minimizing costs. All right, so that's just an idea of what this is about. And so linear program will allow you to find these minimum and maximum values. The shaded area is the solution set and is called the feasible region. Right, so now we're going to take a look at the graphs on page 154 and the feasible region. So what can these graphs look like? Okay, feasible regions, right? In yellow, you have the idea of a bounded region. You have three linear equations that are constraints. These are the constraints. There's three vertices, and the shaded area in the middle is the feasible region of production and the possible maximum values, maximum and minimum, minimizing costs, maximizing profit type of ideas. This is a bounded region because it's all closed in. This has three constraints, but two of them are parallel lines, so it's unbounded going down there. So whenever you have an unbounded, there's either only going to be a minimum or only going to be a maximum. And basically what you do is plug in a point that's going to be way into the feasible region and see if you get a number that's bigger than what you're getting for minimum and maximums, right? So we'll go over the example, but bounded and unbounded regions, right? Those are possible solutions that you're going to get as you graph. So the vertices of the feasible region will tell you the minimum and maximum, and this is optimizing, finding the minimum cost or minimum costs or maximum profits, the minimum maximum values, and they are going to be found at the vertices or in the unbounded region. So here is a bounded example. Example 1 is bounded. So graph it, find the vertices, then find the minimum and maximum values. So we have so graphing it, finding the vertices, then find the minimum maximum. So you have you can see in the example in the book, you have three equations. You have this, and you have this. Right? What do you do with that? How do you look at that? Great example, because you're going to see these and you're going to need to know what to do with that. Right? So what do you do with that? You look at it this way. That's one of the equations. Y is greater than or equal to 3. And then you look at it this way. That's the other end of the equation. Y is less than or equal to 6. Okay? We should know that x equals a number of equations are vertical and y equals a number of equations are horizontal. So we're basically going to look to graph these. I'm going to graph those two in red and shade their areas. So y is greater than or equal to 3. Horizontal line through 3, it's equal to, so you're going to have a horizontal line. Greater than is shading above. y is less than 6, 3, 4, 5, 6. So you have a horizontal line through 6, and that's less than or equal to, shaded below, and the less than, the equal to, is the solid line. So far we have a feasible region that's in here, between the two horizontal lines. They're parallel to each other. All right, and then in blue, y equals 3x plus 12. So I already have kind of points graphed in blue. 3x plus 12, there's plus 12. 3x is up 3, right 1, but we don't want that. We want down 3, left 1, down 3, left 1, down 3, left 1. It's less than or equal to, so the equal to is telling us to have a solid line. Less than, again, is where is the y-axis, less than the line. So less than where the y-axis, less than the line down here. So you're going to shade this side. So remember, the two horizontal lines, the shading we have is in here. Right now this is blocking it off this way and making only there, but still only in those red areas. Now the black one, y is less than or equal to negative 2x plus 6. I have a y-intercept already graphed. Down 2, right 1, down 2, right 1, down 2, right 1. So this line is going through these points. And it is asking where the y-axis is less than the line. Where is the y-axis less than the line? Over here. Okay, so 4 things make a feasible region. The 4 of them are, I don't have any green up there, so you have this barricade right there, right, in the book called Constraints, in the picture that I showed you too, and then this barricade right here, that's this part of this line, and then the top is the y is less than or equal to 6, the bottom is y is greater than or equal to 3, so we have a trapezoid type looking thing that is all shaded up in the middle. Okay, with this one, can we get vertices from the graph? You look at the graph, this point met there, so that is 1, 2, 3, negative 3, negative 3, 3. Right, I gotta go back over here and move up. So negative 3, 3 is the bottom left point, and then do we have a top left right point? Top left point, right, the slope of this line met this right there, so that's negative 2, 6, negative 2, 6, negative 3, 3, negative 2, 6, and then the y-intercept of this line met this here, so that's a 0, 6. So those 3 come from the graph, right? So there's 4 vertices. The missing one is over here. It's in the middle of these boxes, so you need to find that. So what exactly is that? Well, this was in black, and this is in red. That is the y is greater than 3, and the line in black. So basically, on the right underneath the vertices from graph, example, find the 4th point. So I took those 2 lines, the equations of them, and solved them as a system of equations, setting up, we don't need another example fully done out of that, but this equal to this here, and subtract 6 from both sides, divide both sides by negative 2, x is 1.5, then I went back to this equation here because it has an x variable, and plugged in the 1.5 and got 3. So 1.3 and 1.5 and 3 is the 4th point. Okay, so we had 3 points, and now we have a 4th point. So when the region is bounded, like it says in the top of example 1, you have 4 points of intersection. So 1.53, get that in there in red. 1.53 is this one. All right, so now you have 4 points. So you're given an equation in f of xy. Right now, plug all 4 points into f of xy to find the minimum and the maximum. Plug in all 4 points. So to try to minimize my walking back and forth, 0, 6. So 0, 6 is one of the points. I don't know why I didn't write the 0 in there. So 0, 6 is one of the points. So plug in 0, 6 for x and y, 0 for 6, 0 for x, 6 for y. 4 times 0 is 0. Negative 2 times 6 is minus 12, so that's a negative 12. So there you have one of the 4 values. Plug in negative 2, 6 in for f of x, y. Negative 2 for x, 6 for y. Negative 8 minus 12 is negative 20. So a second value that could be a minimum or maximum. Negative 3, 3, negative 3, 3 plugged in for x and y. Negative 12 minus 2 times 3 is 6. That's negative 18. Okay, so that can't be the minimum because we already have a negative 20 of a minimum. And I got to slide up a little bit for this. And 4 times 1.5, 1.5 is 3, 2 3s is 6. So 6 minus 6 is 0. So when you look at the 4 values that we have in boxes here, negative 12, negative 20, 18, and 0. They're all, these 3 are negative, that's not negative, so that is the maximum, because that's the biggest one. So which one of these is the minimum? That would be that, the minimum. Minimum. All right, so what points are these? So the way you would write the answer is at minimum at negative 2, 6. So you have a here negative 2, 6, a minimum of negative 20. So you have a minimum of negative 20 at negative 2, 6, and a maximum of 0 at negative 1.53. Okay, so you're optimizing, finding the minimum, optimum values, the minimum and maximum of those. I'm at 13 minutes on my video, and as you know from class, I can only post 15 minutes at a time from my phone. So example 2 is an unbounded region that I will follow up with part 2.